Hey everyone, and welcome back. Today we are going to tackle something you literally use every single day, probably without even thinking about it. Spherical mirrors. Yeah, I'm talking about everything from your car to giant telescopes. So let's dive in and break down just how these curved surfaces bend light to shape the world we see.
So, have you ever really stopped to think about that? Why does a makeup mirror zoom right in on your face, while the mirror on your car gives you this super wide view of the road? Well, the secret is all in the curve, and trust me, by the end of this, you are going to get the physics behind it perfectly. All right, so here's our game plan for today. We're going to start with the basics. What are spherical mirrors? Then we'll dissect them, look at the anatomy. After that, we'll get into the principal focus, super important stuff. We'll touch on rays and a few imperfections. Then we'll see where these things pop up in real life. And to wrap it all up, I've got a quick guide to help you nail those exams. Sound good? Let's go. Okay, let's jump right into section 1. What are spherical mirrors? Let's just get the basic idea down before we get into any of the more complex stuff. Honestly, it's pretty much as simple as it sounds. Just picture a big, hollow glass ball, right? Now, imagine you just slice a piece off. Then you coat one side of that slice to make it shiny and reflective, and boom, you've just made a spherical mirror. It really is just a piece of a sphere. Now, here's where it gets interesting. Depending on which side of that slice you make reflective, you get two main types. If the reflection happens on the inner, caved-in surface, think of it like looking into a cave, right? That's a concave mirror. But if the reflection is on the outer, bulging surface, that's a convex mirror. And believe me, this one little difference completely changes how they create images. It's everything. All right, on to section 2. To really get a grip on how these mirrors work, we gotta learn the lingo. Think of these next few terms as the absolute building blocks for everything else we're gonna cover. So let's break down the anatomy of a mirror.
First up, we have the pole, which we always label with a P. The easiest way to think about it is that it's just the exact center point of the mirror's shiny surface. It's basically our starting point for all our measurements. Super simple, right?
Next up is the center of curvature, or C. Okay, remember that hollow sphere we imagined our mirror was a slice of? Well, C is simply the center of that original imaginary sphere. It's a really key point. And you'll notice that for a concave mirror, C is out in front, but for a convex one, it's kind of hidden behind the mirror.
So if C is the center of our big sphere, then what's the distance from that center to the edge of our mirror? You probably guessed it. It's the radius of curvature, or R. Now, this R value is super important because it tells you exactly how curved the mirror is. A really big R means it's a gentle, flatter curve. A tiny r means it's curved really, really sharply.
And finally, for our anatomy lesson, we have the principal axis. This is like the main reference line, the absolute backbone of all our diagrams. It's just a straight line that passes right through the pole, P, and the center of curvature, C. Pretty much all the important stuff we're about to talk about happens along this axis.
Okay, moving on to section 3. And guys, this is where the real magic happens. We are talking about the principal focus. I'm not kidding, this is probably the single most important property of any mirror because it's what determines where and how an image gets formed.
So here's the deal. Imagine a bunch of light rays, all traveling parallel to that principal axis, and they all hit the mirror. What happens next? Well, they all reflect and bounce towards a single, special point on that axis. For a concave mirror, they actually meet up. They physically converge at that point. We call this a real focal point. For a convex mirror, they bounce outwards, and it just looks like they're coming from a point behind the mirror. That's a virtual focal point. But either way, that special spot is called the principal focus, and we label it with a capital F.
Okay, and that distance from the pole, P, all the way to this principal focus, F, we call that the focal length, written with a lowercase f. It's a crucial measurement. And here's a super handy rule you have to remember for spherical mirrors. The focal length is always exactly half the radius of curvature. So little f equals big R divided by 2. Easy.
Just one more quick definition here, the linear aperture. Don't let the name scare you. It's literally just the diameter of the mirror's reflective area. It just tells you how big the mirror is, which, tells you how much light it can scoop up.
All right, section 4. This is where we shift from a perfect, ideal world into, reality. See, in a perfect textbook scenario, every single parallel ray hits that focus point perfectly. But in the real world, spherical mirrors have a built-in flaw. And to really get why, we need to talk about two different kinds of light rays.
So take a look here. The light rays that hit the mirror really close to the principal axis, those are called paraxial rays. These are the good guys. They behave exactly like they're supposed to. But the rays that hit the mirror way out at the edges, those are called marginal rays. And yeah, these are our troublemakers. So what happens when our good guy rays and our troublemaker rays don't play nice? Well, the fact that they behave differently leads to a pretty common problem, an optical defect called spherical aberration. And this diagram shows it perfectly. Look, the marginal rays, the ones from the edges, they get bent way more sharply and end up focusing closer to the mirror at a point we can call FM. Meanwhile, the nice paraxial rays from the center focus farther away at FP. So what's the result? You don't have one single sharp focus point. You have a messy spread of points, and that makes your image blurry. And here's a cool little tidbit. This is exactly why super high-end telescopes, like the Hubble, don't use simple spherical mirrors. They actually use parabolic mirrors, which are shaped just right to force all the rays to meet at one single perfect point. It's a really clever fix for this exact problem. Okay, enough with the diagrams for a minute. Section 5. Let's bring this all back down to Earth. Let's connect the theory to the real world and finally answer that question from the beginning. Where do you actually find these mirrors in your daily life? Well, they're everywhere. Those makeup and shaving mirrors that let you see everything up close, those are concave mirrors. You put your face inside the focal length and boom, you get a bigger magnified image. What about your car's side view mirror? That's convex. It's designed to give you a really wide field of view so you can see more of the road, even though it makes cars look a bit smaller and farther away. And of course, the big ones, giant concave mirrors are the heart and soul of huge reflecting telescopes, gathering up all that faint light from stars billions of light years away. Okay, final section. Let's switch gears into exam mode. For all of you out there studying for a test, this is your cramp session. Let's do a rapid-fire review and make sure you've got the key concepts locked down. First things first, definitions. You absolutely have to know pole, center of curvature, principal focus, and focal length. Know them by heart. And definitely don't forget spherical aberration. I promise you, it's a classic exam question about why these mirrors aren't quite perfect.
Next, you need to be able to explain the big ideas. So if a question asks, why does spherical aberration happen? You say, because the marginal rays focus at a different point than the paraxial rays do. If it asks, what's the relationship between the focus and the center of curvature? You know the answer. The focal length is half the radius of curvature. F equals R over 2. If you can explain those two things clearly, you are going to be in fantastic shape.
So let's end on this final thought. I know it can seem like just a bunch of lines and points on a diagram, but truly, understanding the geometry of a spherical mirror, that is the key to unlocking the entire world of optics. Once you master these fundamentals, you've built the foundation to understand everything from how a camera works to how those incredible telescopes let us look back at the beginning of the universe. Thanks so much for joining me.